Yes. So recall, what are we trying to do? We want to prove when Q, so let's go all the way back. We were looking at this, yeah, we were looking at progressions, sum over primes congruent to A mod Q, 1 over P. This diverges as long as we can do the class number formula. Exactly.
Non-vanishing of L1 chi.
Exactly. L1 chi Q, it doesn't vanish. And the way that we're going to show this, when Q is, so we did the case when Q is 3 mod 4. When Q was 3 mod 4, then the discriminant was minus Q, because that's 1 mod 4.
Discriminant.
The core of the corresponding character. In other words, this then when Q is 3 mod 4, we're dealing with definite binary quadratic forms.
Right.
And when Q is 1 mod 4, when Q is 1 mod 4, that's what we have to show. And then what we want to show is that this is equal to the class number h of Q times log epsilon Q over square root of Q. It doesn't really matter what it is for the purposes of it being non-zero, just the fact that this is non-zero. Yes, exactly. So epsilon, let me switch to D. So D is now equal to Q, which is 1 mod 4. Epsilon D is T plus root ds over 2, where T squared minus ds squared is 4, is the minimum solution, L solution.
Wait, and we did.
This is the claim. This is Dirichlet class.
We were saying for both cases, or for the
for the
1 mod.
For the 1 mod 4. For the when Q is 3 mod 4, in other words, D is negative, then L1 chi was equal to just the class number h of negative D or h of Q. I don't know what you want to call this, h of negative D. Well, D is negative, h of negative Q, h of negative Q divided by root Q with maybe a pi somewhere. So that's what this is what we already proved.
Right. And that connection we saw it with
Heegner points. With the roots of the quadratic. I'll review that proof. And this is what we need to do today.
Yeah.
Okay. Right. So let's remember how this proof went for a second, because that'll be useful. We started with the Eisenstein series, E of Zs, which is sum over gamma in SL2Z mod gamma infinity, imaginary part of gamma z to the s, at least when real part of s is bigger than 1.
Mm-hmm.
We showed the analytic continuation of this. This has a simple pole. That's one way. Yeah, I guess I never showed you other proofs, and now we're out of time. This has a simple pole at s equals 1, and the residue, it doesn't really matter. The residue is a constant. I mean, that is important. The fact that the residue as a function of s, the residue at 1 is a function of z. That function of z is a constant in z. That is used essentially, it's actually 1 over the covolume, which is, you guys know the volume of the fundamental domain.
It's like pi 6 or
yeah, pi over 3, it turns out. That's just from Gauss-Bonnet. If you have a hyperbolic triangle, do we know this? Do we talk about Gauss-Bonnet at all?
You can just integrate it like straight, right? There isn't.
You can integrate it, yeah, you can integrate it directly, but a more general, okay, so just for your, the Gauss-Bonnet theorem, it's kind of amazing. Gauss-Bonnet says that if you have a triangle, I'll draw it in the, any triangle, it can have an ideal vertex, it doesn't have to. If it has, that's not a triangle. Too many edges. Okay, I need to fix that edge to go through there. Okay, if these angles are alpha, beta, gamma, so gamma here is 0, then the area of the triangle is pi minus alpha minus beta minus gamma. So in fact,
hyperbolic geometry?
In hyperbolic geometry, exactly. That's why I'm drawing it in this, in the Poincare disk. So in fact, in hyperbolic geometry, angle, angle, angle is not similarity. It's congruence.
Whoa.
There are no similar triangles in hyperbolic geometry. If the three angles agree, then the triangles are congruent, and the side lengths are the same.
That's insane.
Yes, so that actually already even Gauss and Bolyai and Lobachevsky sort of, this was the first thing that, this is how people were trying to come up with a contradiction
To like the parallel.
to the lack of the parallel postulate. They said, if the parallel postulate fails, then angle, angle, angle actually implies congruence instead of
And so they just got a
similarity.
whole other theory that worked.
well, they were trying to find a contradiction, but they couldn't make it work.
Insane. And
So,
then- and it's all in radians, you're saying here.
yeah, that's right. This is measured in radians. Okay, so an ideal triangle. So an ideal triangle. What's the area in here?
Wait, like I
Pi.
trying to.
Pi. Yeah, all ideal meaning all the vertices are at infinity.
Right, yeah. Yeah.
So all these angles are zero, so this area is pi.
So max area a triangle can have is pi.
That's exactly right.
So
A hyperbolic triangle can't have area larger than pi. But this one we have pi over 3, and 0. So what's left over is pi over 3. Okay, and you can prove this by, this is an easy thing to prove. Whenever you have a triangle like this, you can cut it. Okay, let me not go into the proof because we have other things that we want to do. But it's just as easy as computing this by hand. In other words, using dx dy over y squared.
Without integrals.
No, with integrals. No, you do an integral. In order to prove this formula, you can do an integral where you take an arbitrary triangle and turn it into triangles that look like this by Mobius transformations, which preserve the area,
I see.
and then compute the integral there and just say, okay, that's what it was in general. This wasn't about the fact that this is root 3 over 2 or something. It's just-
That's what you're saying, that this is just really an extension of like this.
Yes. The same calculation that gives you pi over 3 will give you Gauss-Bonnet if you do it slightly more generally.
Very cool.
So, all right. Right. So we had this Eisenstein series.
Can you turn this
It's-
into some like quadratic form? So
Yes, exactly. Its pole at s equals 1 is a constant, which means if we sum over, so now we have our, let's go slightly slower. This is still all recall. Recall what happened when the discriminant was negative.
Mixed fault methods.
Yes, if you like. We looked at the set of all quadratic forms, not up to equivalence, just all of them, of discriminant d squared minus 4ac. It's d, and of course primitive. Okay, if d is fundamental, then it's automatically primitive. ABC equals 1. Primitive as a binary quadratic
Right,
form.
right, not in the other.
Right.
sense.
And the class group, or the class set, since we haven't given the group structure, never mind. So there's an action of SL2Z on this space, right? By composition, gamma, Q composed with gamma gives you something else that has the same discriminant, because the determinant of these things is 1. And this is in the narrow sense as opposed to GL. So gamma is SL2, PSL2, depending on the context.
Factors of 2.
Yes. So what's the class group? It's this whole set divided by the action of gamma. Okay, and the size and the class number is exactly the size of this thing. It's the size of the class group. These are the inequivalent forms, exactly. And each form gives rise to a number alpha q, which is the root, which if d is negative is in the upper half plane. Right? And so then we took the Eisenstein series at these roots, alpha q, summed over some set of representatives. So this is invariant under the action of gamma, so we can actually take the classes, the inequivalent classes. This is what we looked at.
Right.
And because the residue at s equals 1 is a constant, independent of z, so if we take the residue of this sum, the residue at s equals 1, will be just some constant, the same 3 over pi, times the number of contributions. They don't change, they don't depend on the value of alpha any longer.
If it weren't for that, then like
If-
it'd be toast, right?
Well, I mean, this is a modern proof. Dirichlet had a proof that didn't use Eisenstein series since Eisenstein wasn't born yet. For a lot of reasons, Eisenstein not being born being the least of them. So we get exactly the class number on this side, right? I'm just reminding you.
Right, because the alpha q somehow is going to encode the quadratic form itself.
That's coming in a second. That's coming in a second. Right now, all I'm saying is that the residue at s equals 1 is a constant, is the constant function. In Z,
Oh, right.
this
you're
is
right,
independent of Z. So this is independent of Z. So it doesn't matter which point you took, it's the same constant, and this is a finite sum. Okay, so the residue is just how many points there were in the contribution times that constant. The residue at s equals 1 equals this thing. The residue at s equals 1 of this expression
Wait,
is
how
equal
did
to
we
this.
turn it into a sum of their classes?
We just said, look at.
Oh, yeah, right. Oh,
Look
yeah,
at this
because
thing.
E is a sum itself, but yeah.
E is a sum itself, but now we're summing over the classes of these unit points.
Right.
The Eisenstein series evaluated the unit points. When we take the residue, it doesn't matter where we evaluated.
Correct.
You just get a sum of however many terms there were, which is the class name.
Yeah.
Okay, now we also, if you open this a little bit, so this is Q again in the class group is X mod gamma. The Eisenstein series itself is a sum over gamma in gamma mod gamma infinity of imaginary part of gamma alpha Q S. Exactly, but before, so yeah, we can do this in a variety of ways. One way is before unfolding, sorry, what's imaginary part comma S, imaginary part to the S.
Right.
This is a number, this is to the S.
Right.
Okay.
We have an expression for that.
Exactly. We know what that is. The imaginary part, let me remind you that the imaginary part of GZ, exactly. So this, I want to remind you of a slightly more general formula, which we did prove, which is that if G doesn't have determinant 1,
Right.
the determinant is what pulls out.
Yeah.
In general. Okay, so this thing, again, I'm just reminding you, the imaginary part was root D over 2A. So it's root D over 2A to the S, divided by the norm squared of, exactly as you said, CZ plus D, C alpha Q plus D. And we worked out that this, in fact, is nothing but Q, because it's C alpha Q plus D times C alpha Q bar plus D, this norm square. So this thing is actually 1 over Q itself evaluated at CD to the S with no absolute values. That's exactly what Q is. Actually, you have to pull the A, the 2A, you have to pull the 2A inside of here to get that. Okay. Exactly. So the D, so the root D to the S pulls all the way out. Then we had a sum over Q in XD mod gamma, a sum over gamma in gamma mod gamma infinity, and just a 1 over Q of CD to the S. Okay, so this inner sum was like a Epstein zeta function. Epstein zeta function for Q. And then we observed that's the same thing as Q composed with gamma. This thing is the same thing as Q composed with gamma of 0, 1.
Yeah, this is a linear change of variables.
Exactly. So if we're going to sum over Q up to gamma and gamma up to gamma mod gamma infinity of Q composed with gamma, well, that's the same thing. So this root D to the S is just there. That's the same thing as summing over Q in gamma D mod gamma infinity. So we unfold these two. This is just, it's been a while since we did this. So I want to remember, we're going to have a slightly more technical computation to do in the positive discriminant case. So I want to have this firmly in your minds as we do it. And then just 1 over Q of 0, 1 to the s. Right? Now this space, let me put it here somewhere, x of d mod gamma infinity, we worked out is the set of all ABC with discriminant d, b squared minus 4ac equals d, but with the action of this translation, this gamma infinity, means that we can move b mod 2c. So b is determined mod 2c. Okay, so B.
Choice of representative.
Exactly. The choice of representative is up to the choice of B in a residue class mod 2C. Okay, so we could write this as a sum 1 over d to the s, a sum over the value of C, 1 over, by the way, this is C, Q of 0, 1. Q is ax squared plus bxy plus c y squared. Y is the only thing that survives. So I get a 1 over c to the s times r of c, where r of c is exactly, given a c, for fixed c, it's the number of, well, b mod c, mod 2c, so that there exists an a with b squared minus 4ac equal to d. I know I'm going fast, but we did all of this already. And then we saw, if we look at, this is a multiplicative question. If you look prime by prime, or look at the divisors of.
Grouping them by c, so you could get multiple c's with the same, multiple terms of that sum with the same c, right? And so
That's
you're
right.
just grouping those together.
That's right. Group by the possible values of c. For any fixed value of c, how many terms do we get? We get this divisor sum, which was captured exactly by the Dirichlet character of discriminant d. And so this sum, if you unfold this sum, so this sum was a sum over c, 1 over c to the s, and a sum over L dividing c of chi of L. But that's the same thing as this Dedekind zeta function. So this opens as zeta of s times L of s chi, which is also, as an aside, the Dedekind zeta function of the field. Okay. Oh, good. Good. Where K is Q adjoint with D. Okay. And now we're done. The reason we're done is now we take residue at s equals 1 of this thing.
And zeta is 1.
The zeta gives us 1. This gives us whatever L of 1 chi is. And this gives us root d.
Which is already equal.
So we can, exactly, we compare that to the other side, we get class number times a constant. So the L function at 1 is class number over root d with some constant, which is pi. And there's some, I've been a little fast and loose with the number of, for d equal to -3 and d equal to -4, there's some extra multiplicity from the larger group of units.
Right, it's just the fact that phi is small enough for 3 and 4, and then like
right.
For bigger ones. Then
Yeah, so this is really for d less than -4. Yeah, the 3 is supposed to fall out somewhere. So I've been a little sloppy with maybe there's a 3 here. Somewhere I've lost a constant. But it's the point is it's some constant times hd over root d.
The units has to do with the degree of the extension, right? But you can't have too many units because otherwise it would imply that you're really separating over some higher degree superforming problem.
You're asking about the unit group of this. So
no, were you saying the 3 and -3 case and the 4 case? They have more units because they're allowed to have more units.
Well, they have more units just because there are more points on the circle. Only in the rational solutions, the algebraic solutions to triangles with, there's only 30, 60, 90 triangles, or 45, 45, 90 triangles are the only. No, but really what's going on is if you're, so for most fields, your unit group will just be ±1.
Right.
Because the other points in the ring of integers will be too far away from there. But when you have the Gaussian integers, you also get I and minus I.
Yeah.
And when you have the Eisenstein integers, you also get the 6 groups of unity.
Hexagon.
Yeah, you get the hexagon. So that's the only difference in this constant.
And so in those cases, you just have to add that constant and nothing else.
That's right. That's right. So there's a constant here, which there's a W that most people will put, which is about this constant. Okay. So far, so good. So that was a very quick reminder of how this works. So how are we going to do it in the positive D? So what are we going to do for D positive? So instead of what this was asking was about Heegner points. Exactly. We're evaluating the Eisenstein series at these alpha q, wherever they are, in the fundamental domain. Now we don't have alpha q's in the fundamental domain. Now we have exactly. So we still have alpha q. It's the same formula plus root d over 2a, but now this is somewhere on the real line. And of course, we also have its conjugate, which is on the real line. And we have the geodesic connecting them. And we've already talked about the closed geodesic, exactly. So there's some length, L, for which this is a closed geodesic in the modular surface. So if you close this up, whatever it's doing, it'll come back onto itself. Alpha bar is just the Galois conjugate with a minus d. Yeah. So there's for each form.
These should be chosen purely periodic, right? So that it respects this.
That's right.
picture that you drew.
That's right. That's right.
In each class, there's some representative.
In each class,
Yeah.
there is, usually more than one representative, reduced representative. But, so let's, again, it's the XD mod gamma is still the same classes. There's no difference in that. We can still sum over,
Get to do the residue thing again.
we're going to try to do the residue thing, but how are we going to capture this behavior? So if we look at forms in here and we want to sum over these forms, we can't evaluate the Eisenstein series at alpha q. This it doesn't have a, I mean, it's the Eisenstein series was defined in the upper half plane, not in this limit. So instead, what we should do well, but it's kind of an arbitrary thing. Why not integrate along the geodesic? Let's integrate the Eisenstein series along the geodesic. What should I call it? People usually call geodesics gamma, but gamma I want to reserve for something else. G is an element of the group. C for curve, good. C of Q. So each Q gives rise to a curve C of Q. This is our curve C of Q. And I want to integrate this thing. I want to integrate the Eisenstein series along this arc length. That's the right object to take. So you take all these closed geodesics, just like in Duke's theorem. You take all the closed geodesics of a given discriminant, and let's integrate the Eisenstein series along them with respect to arc length. So we have to make sense of all of these things.
Well, we're fine.
Sure. Why not?
Well, I guess like if will the integral always give you, I mean, wait, oh yeah.
It's a finite sum of a compact integral of a
Right.
function, that's.
Because as long as you choose your representative for the upper half plane.
Is it well defined in that sense?
Yeah.
That's exactly right. So it is well defined because these things are all they're all the gamma inequivalent ones. The gamma equivalent ones will have the same values of E, because E is gamma invariant.
Right. And so does it matter where you're integrating?
It doesn't matter which choice of representatives you take, and it doesn't matter where you start and end your integral. If I start it here and end there instead of here to there, that's still the same values of the Eisenstein series.
E was made to be invariant.
So that's why this integral.
Well, it converges because it's a compact integral, right?
It's only trying to get the back plane. Could blow up like this. You can't integrate that idea. We don't know what to tell you.
I'm not integrating over the infinite geodesic curve. I'm only integrating over the length of the geodesic. So the length of this curve has length, whatever LQ is. The length of the geodesic corresponding.
Right, because the whole geodesic has infinite length.
The whole geodesic has infinite length. I'm not integrating the Eisenstein series over the infinite geodesic from alpha bar to alpha. I'm integrating it over the length of the geodesic where it closes.
You're taking the primitive one?
The primitive, exactly, the primitive length. Something you don't like. So that part of it is compact.
Yeah, because to do the whole geodesic, then you
Right,
do
so
infinite
It's
iterations.
a closed geodesic.
Closed
So-
geodesic,
so
yes.
it's- Okay, so it's infinite unrelated.
Yes, closes back up. I'm drawing it in the universal cover where these 2 points and their tangent vectors are identified by gamma.
The segment, it doesn't matter which segment, which closed segment we pick because it's there.
Because E is gamma invariant.
Then you're integrating in the complex analysis sense that we integrate over curves.
So this is with respect to arc length. So let's do all of that. The best way to do this is to do it in homogeneous dynamics where we get that for free. So let's remember a couple of things. Let's remember this correspondence between positive discriminant, in other words, indefinite binary quadratic forms, and hyperbolic matrices. So for Q, whatever, discriminant D, remember we get this hyperbolic matrix M, hyperbolic matrix, and for an equivalence class of Q's, we get a hyperbolic conjugacy class, but the matrix itself is given by T plus DS over 2, not D, D. Am I going to remember this?
And
And then
giving the correspondence itself from the
I'm giving-
quadratic form.
that's right.
Uh,
CS, AS, T, I think this one's a minus and this one's the plus. It doesn't really matter.
Yeah.
T plus BS over 2. I think this is what let's see. Yeah, good. And I have a note that I'm going to get a clash with this complex number S, and I had better change these S's to V's.
That's true.
Okay. Where again, T squared minus D V squared is equal to 4. Is a primitive solution, is a fundamental solution. Fundamental solution. So that I don't go over the geodesic twice. I only want to integrate over the geodesic once. Okay. So this is our matrix in SL2Z corresponding to the quadratic form Q. Given a matrix, we get a closed geodesic. Well, how do we get a closed geodesic? If G in G, which I'm identifying, I'm reminding you, it's all coming together. It's all coming together. This is the unit tangent bundle of the upper half plane. If G in G is the starting point, is a starting point of a closed geodesic, exactly, then the geodesic flow, which is right multiplication by this AT map, right? AT is the diagonal matrix, e to the t over 2, e to the minus t over 2. When I do this at time L, so I'll say when t is equal to L, that's the length, that's exactly the length of the geodesic. I get back to the original point, but an equivalent original point, and the equivalence is exactly this matrix F. Okay, that's what this closed geodesic is. The closed geodesic corresponding to M, so the closed geodesic corresponding to M, starts, doesn't really have a starting point, but starts at G, which is the matrix of eigenvalues, eigenvectors of M. That's what G represents, and has length, exactly. The length is AL, the length is L. But what's the relationship with the trace where, so the trace of M, which is, by the way, T, by construction, exactly this T, is equal to, on the other hand, the eigenvalues of M are e to the L over 2 and e to the minus L over 2. So-
Variance under conjugation.
Right, so it's twice cosh L over 2. And we can solve for L in this formula. So I have T over 2. So what is caution? It's actually better to write out what this is. This is e to the L over 2 plus e to the minus L over 2. It's just the sum of the diagonal elements of this thing. Okay, and this makes it easy to solve for T. If I multiply through, I'll move, I guess I'll move this to the other side, and I'll multiply everything by e to the L over 2. Exactly. So I have e to the L minus e to the L over 2t plus 1 equals 0. I just get a quadratic in e to the L. Okay, so you see what I did here, how to get from here to here. So now I use a quadratic formula. E to the L over 2 is negative, so that's positive t, plus or minus, of course I want plus, because that's the positive solution. Square root of t squared minus 4 all over 2. Hang on a second. What is t squared minus 4? T squared minus 4 is dv squared.
Yes.
So this is exactly t plus root dv over 2. This is exactly the fundamental discriminant. Okay, so now I'm going to take logs.
That's what we're getting the log of epsilon d.
Exactly. So the length will exactly be twice log of epsilon d. Now that's the length of a particular quadratic form. And notice that it only depends on the discriminant, not on the form itself. So the length is actually the same length. All of the closed geodesics of a discriminant d have the same length. Okay?
That's insane. Well, the same
So-
discriminant,
Right.
because this is just a fundamental.
That's right. Okay, so different classes all have the same length. So already that gives us something. What's going to happen when we take, let me call this star.
Wait, so are you integrating ds or dz?
This is an integral. Okay, ds means d arc
Oh, you mean
length.
the arc length. for the
D
verse.
arc length.
Okay, yeah.
It's not dz because dz, I don't know what dz means. I know what dz means if I have a volume, but I want to integrate arc length. But actually this is how you can, this dt is the arc length. That's the beauty of geodesic flow, or the beauty of this being the geodesic flow of time t means you move along a distance at speed 1. Yeah, so it's exactly arc length. So in fact, we can write this. Okay, so let me rewrite star. So star, yeah, it may take less time to actually write it again, is an integral. So let's write this like this. E, the Eisenstein series at, let's call this g of q. So g, because m is really m of q, depending on the quadratic form. We get this eigenvector matrix G, which is really a function of Q. Okay, so we start with this G of Q. We multiply by a T. I can't use T. T is the trace. A U. Okay, and how do I get from something in the in G back to the upper half plane? Just act on I. Okay, so if I take this and I integrate as u goes from 0 to L, L is, I know the length, du.
Correspondence between matrices and
Yep.
and geometry.
Yep. And so what's the residue of this? What's the residue of star as s goes to 1? At s equals 1.
And the compact lines.
It's a nice compact integral and a nice finite sum. The Eisenstein series is being evaluated in a compact region where everything converges uniformly. It doesn't depend on z. So all that I'm going to get is the length times the class number. So I'm going to get exactly the class number times the length, which is log epsilon d.
That's why the regulator shows up.
That's where the regulator shows up. That's one way to get the regulator to show up. There are others.
Now we have to manipulate this again.
Right, times a constant, whatever, 2 over 6 over pi, something. I don't know. I'm just going to say constant. I'll write 6/pi, but don't quote me. Okay,
Now we have to do the other stuff.
now we have to do the other stuff. So far, so good?
I'm a little bit confused with the last thing. So
Yes.
this should be a function of z, right? If we're going to find the residue.
A function of s. If the residue is s at s equals 1.
Okay, okay. So this is a function of s.
Yes.
It does not depend on integrating over here.
I'm integrating over u in a compact integral, and I'm summing over q in a finite sum.
So if we compare this to the non-integral, before we integrate it, like, you just somehow destroy the dependence on z.
That's right. So that's right. There's no dependence on z. So this is some holomorphic function in s. It's holomorphic in s. Meromorphic, because I have a pole at s equals 1.
Okay.
The pole at s equals 1 of this thing is independent of these times how many there were. And the length is independent of which form it was. So you get exactly the regulator, the log, or the fundamental.
What is the residue, like a half or something like that?
Sorry?
What was the residue of?
Of the Eisenstein series,
Yeah.
it's like 3/pi. It's 1 over the volume.
Oh, yeah. That's what it is.
But when we did it, did we add in zeta of 2s or not? When we proved that that
Up to some
formula.
constant.
Yeah, up to constants. I'm not gonna worry about constants. Okay. By the way, back up here, there's something that I mean, I like doing this calculation because it goes through. You see this Epstein zeta function piece, but we could have done something much earlier to get to this stage.
I mean, from the.
Just from this point of view, we could have noticed that this imaginary part is also the imaginary part of alpha. Remember, gamma acting on alpha q is the same as alpha of q composed with, I don't know if it's gamma or gamma transpose or something. Let's just say gamma to the s. Gamma inverse, fine. It has to be because it's on the other side.
Yeah,
So already at this stage, we could have unfolded.
yeah, that's true.
Because it's all q's and gamma. And then when we unfold, what do we get? We just get the imaginary part. So this is the imaginary part we're at the identity element, at the identity coset. In other words, this thing is, I don't know where to write it, but the imaginary part of alpha gamma is exactly this. I mean, with this factor of d to the s. So we could have done that from the beginning, but now let's here we really want to use that idea. Okay, we need to know what G is. We need to know what G is. So let's work out what G is. This G, the eigenvectors of M. Okay. Let's do a side calculation. So if M, I'm going to get in trouble again with letters, but I'm going to write A, B, C, D just in this little region as A, B, C, D, because later I want C and D to be, I'm going to open up this Eisenstein series. Yeah, you'll see. I think I can get away with it. So if M is A, B, C, D, then, and it has eigenvalues lambda, determinant 1. So eigenvalues, let's say lambda and 1 over lambda, because the determinant is 1. 1 over lambda must be lambda bar, the Galois conjugate. We can work out what lambda is. I mean, it's not hard to see. Okay, fine, just do it. A minus lambda, B, C, D minus lambda. The determinant is A, D minus trace lambda. Exactly, minus BC equals 0. And exactly as you said, that's 1. Okay, so lambda, in fact, is equal to t plus or minus square root of t squared minus 4 over 2. Well, we knew that already. This lambda is e to the L over 2 in our setting. That's the positive eigenvalue, and its Gauss conjugate is this negative eigenvalue, which is the regulator, the fundamental unit. This is epsilon d. Okay. Right. So so now we need to work out what so if I look at m minus lambda, what is the vector that's sent to 0? I need to find the eigenvector of eigenvalue lambda. Okay, so that means I need a linear combination of a minus lambda b c d minus lambda, which will go to 0. Well, knowing that this thing is singular, I just need one vector here, and that'll do it. So why don't I take lambda minus d and minus c? That's going to clear the bottom, and we can work out the equation, but it has to clear the top because this is a rank 2 matrix. So mn is rank 2, so m minus lambda I is rank 1. So if you clear the bottom, you have to clear the top. Okay, so this is an eigenvector. And of course we have the other eigenvector with a 1 over lambda bar. So G, we can actually take G. Oh, sorry, this is a plus C. I don't need the minus sign here. I just need to change one of the signs. Yeah, I already changed the sign. So we can take G to be lambda minus D C, lambda bar minus D C.
What is G to the third?
G is the matrix of eigenvectors. What I'm saying is, so let me make this an exercise. I think we need to spend the time to do it. G times e to the L times G inverse is equal to M, where L is the, e to the L over 2 is the eigenvalue. Okay, so we've made a particular choice. By the way, this does not have determinant 1. This is in GL. Yeah, this is in GL2 plus R. But it doesn't matter because whatever the action is, it is. Okay.
It's not.
That's right.
Yeah.
That's right. It's not normalized. Well, what does that mean? This gives us, so for G, so what is G corresponding to? Okay, so this is the end of where ABCD is used for M. Remember, M was T minus B V over 2 negative C V. This is a capital C, A V, and then T plus B V over 2. So what is the G of Q? This is M of Q, where Q is ABC, the quadratic form ABC.
AB in the bottom row.
Right, I have lambda. Lambda is epsilon D. So I have the G will be epsilon D. Well, let's write that what that is. D plus root D, T plus root dV over 2. That's lambda. Minus D, T plus BV over 2. C is AV. Yeah, CV is another AV. And here I'll have lambda bar minus D. So lambda bar is T minus root dV over 2 minus the same thing. Okay. Let's keep going. D, the D entry is this T plus BV. Okay. So the T's cancel. And I just get negative BV plus root D over 2. In fact, since I only care about this up to GL2, I can multiply everything through by V.
Where did V come from? V was the.
V is T squared minus DV squared is equal to 4. I was forced to change away from S's.
Yeah.
So far, so good.
Is it in multiply through, you mean pull out the V's?
I can pull out the V's. So let's do 1 over V. I can multiply by any constant since I'm not worrying about the determinant. Let me throw in this 1 over V
Oh,
on
right.
everything.
This is what you're conjugating by, so. the
Yep.
constant totally just dies out.
Yep. So far, so good?
Yeah.
Okay, so I have this GQ. I have a T over 2 minus T over 2, so that's gone. I have a negative B plus root D over 2. In fact, let me also divide out A,
We assume it was non-zero.
which we assume is non-zero. Yeah, so I can make this bottom row 1, 1.
All of a sudden, this looks like.
And over here, I get the same thing, but with a minus D.
All of a sudden, this looks like alpha.
This looks exactly like alpha. So this is alpha 1, alpha bar 1.
You can choose this as a basis of eigenvectors.
You can choose this as your base point from which to do, I forget who, Nick or somebody said, when you have this alpha and alpha bar, you could choose like some point as a midpoint.
Right.
This is a very good choice
To start from.
Now, I don't know where this is. I don't think it's up here. I think wherever this is, wherever this GQ is, it's somewhere. But how can we immediately see that it indeed goes to alpha at infinity and alpha bar at minus infinity? Just act on e to the, act by at on I
Yeah.
and see what happens for large values of t, right? So what is that? This is, so first of all, this is just e to the t times I, because there's an e to the t over 2 on top and on bottom, az plus b over cz plus d. So this thing times g is an alpha e to the t times I plus alpha bar over 1 times e to the t times I plus 1. Right? G is A, B, C, D. So I get AZ plus B over CZ plus D. And the Z is e to the t. So as t goes to infinity, this goes to alpha over 1. That's the forward direction. As t goes to minus infinity, these parts die, and this goes to this. This is described there, yeah. All of this stuff is, it's funny, all of this stuff is completely classical, I think, in my mind, and yet I have no idea what a good reference for this point of view of Dirichlet's theorem is. Lewis, I don't know if you have seen this presented this way.
Yeah, it's a good question. So like I wouldn't say it was like exactly this way, but my reference was George. So George basically wrote out a proof and sent it to me once that looked like pretty similar to this, but I don't think he was doing it exactly the same way. He was doing some of the details different. Yeah.
Great. Okay. So indeed, this is a good starting place, or it's some starting. It's as good a starting place as any. This matrix is as good a starting place as any. Will flow by time L, and that's how we parameterized this this integral here. So let's go back to this. Okay. I'm going back to this. So far, so good. I'm not going too fast.
Now the point is to calculate it differently, right?
Yes. Now the point is to calculate it
So
differently.
I thought, well, you know the answer. Why do we keep going? Calculate differently compared to the answer.
That's right. That's right. So one answer is this, whose residue at s equals 1 is this h times the regulator. And now let's calculate it another way. So exactly. So star of s again is a sum over q in xd mod gamma. The integral, at first the integral, the first version of this was that we had a different integral for each q, right? This curve depended on q. But now that we've parametrized it, the length doesn't depend on q. So actually this integral we can pull outside. So the length is out here. And what's inside is the Eisenstein series at all of these things. And let's remember what the Eisenstein series is. It's a sum over gamma in gamma mod gamma infinity of the imaginary part of gamma z to the s. Gamma z, z is GQAUI, GQAUI to the s.
Why did you say you could pull the integral through?
So the integral originally, as originally stated, the integral was over the closed, like each closed curve, which of course depends on Q. When we parametrized it with this parameter U,
You made a choice.
we made a choice of the starting position, of course, depends on Q, but they all have the same length. Independent of Q, only depending on the discriminant.
Okay.
So I'll pull that integral. There was an integral in between here, and I pulled it to the other side of Q. Okay,
Works out the same.
right. Okay. So let's work out what this is. You guys starting to see any similarities or, well, let's see.
This G already is encoding that alpha that we lost from the board.
How? Yes. No, it's exactly like that. It's exactly like that because look at what G is. It's alpha alpha bar. When you change Q by, if you change Q, if Q gets replaced by Q composed with gamma, what happens to G? G of Q composed with gamma is what is it, gamma inverse or something? Yeah, let's put gamma inverse, fine. Is gamma alpha 1, gamma alpha bar 1, because the alphas change. Right? Alpha of, what is it? Alpha of gamma composed, Q composed with gamma inverse is gamma acting on alpha Q. That's true regardless of whether alpha is in the upper half plane or in the real line. Right? That transformation.
Wait, I'm a bit lost. What are we doing?
So I'm trying to, so there are several things we could do here. We could open this up and try to interpret it as an Epstein zeta type function, or we could unfold it immediately
Sure.
and see a slightly simpler computation.
How are you trying to unfold it? I guess that's what you were saying.
Right, we have this gamma.
Yeah.
The gamma only depends on CD, and it's hitting this G of Q AUI.
Mhm.
So if you try to work this out, well, let's work it out. Let's work it out. It's not too hard. Okay. So if we work out what this is, gamma times, okay, so AU times I is just e to the UI. That's easy. Let's,
That's about.
as a element in the upper half plane. So this is an action. This is matrix multiplication, and then this is action.
And I is the vector II.
No, this is projecting from the unit tangent bundle just to the space itself. So I'm forgetting the tangent vector. It also acts on the element II. I'm forgetting about the second component. I don't care about the tangent vectors. The Eisenstein series isn't a function on the unit tangent bundle. It's a function on the universal cover itself.
Oh, okay, so I was pitching.
I don't care what the tangent vector is at the moment. Of course, there's another way if you want to capture it.
So you're taking the action to just be the first. Oh, okay, that action.
Yeah, well, that's what the Eisenstein series is, right? The Eisenstein series is imaginary part of gamma z to the s, where z is a point in the upper half plane, not in the tangent bundle of the upper half.
Right.
Okay, so how did we get from this? Well, this is the whole point is how are we going to parametrize integrating over this curve? We can't take values at infinity, this alpha and alpha bar, and stick those into the Eisenstein series. We're going to take some finite piece of the curve, and that's what we'll integrate against. And then what we realize is the way to parametrize it is to start from this GQ, flow by the geodesic flow by time u, and integrate as u goes from 0 to the length. That's exactly capturing that.
Yeah, and we're only integrating positions is what you're saying. We're not, we positions and directions.
Exactly,
So
exactly. So this has already forgotten about the unit tangent vector.
this is just by design, how you set it up.
This is, yeah, this is because the Eisenstein series is a function on the cover and not the tangent bundle of the cover. So far, so good. Okay. So this is e to the u times I. Now, gamma times, yeah, let's work out gamma times g. We only need the bottom rows of this. Because the imaginary part, so I want to use this formula that the imaginary part is equal to, right, it's only it's only the bottom row squared. Where was it? Here, it's this bottom row squared. And let's remember, because one of these matrices does not have determinant 1, that we have to keep track of the determinant.
Yeah.
Okay. So, so I need to work out somewhere off to the side. Fine, I'll do it here. If I have gamma, which is some CD times G, which is alpha, alpha bar 1, 1, what is its bottom row? Okay. Yeah, C alpha plus D. Oh, that's good. And C alpha bar plus D. So in fact, this whole imaginary part is equal to the imaginary part, the original imaginary part, which is just e to the u. Okay, so I think I can do this computation all at once. The original imaginary part is e to the u. I divide by the norm squared of c, which is a real number. Z is e to the u I, plus d, which is c alpha bar plus d, norm squared. And then this whole thing is raised to the x power. So this is the original imaginary part, c, z plus d, norm squared.
Right, this is the gamma of.
So gamma g, we just worked out what the bottom row of gamma g is.
That's what we were saying with gamma.
Exactly.
Then, okay. Maybe even,
So this is a matrix times this complex number, e to the ui. The fractional linear action is the original imaginary part, in other words, the imaginary part of e to the ui.
oh, right. Just instead of SL2, maybe you're a little different, right? GL2.
Very good. I was waiting for someone to remind me that G does not have determinant 1.
Right, so, but you can still do the action.
You can still do the action. We just need, in the formula, we just need the determinant of G. Now, what is the determinant of G?
In this case, it's alpha minus alpha bar.
Exactly. So determinant of G is alpha minus alpha bar, and that is negative b plus root d over 2a minus negative b minus root d over 2a.
Oh, wait, so you use the imaginary part. I mean, well, the conjugated part.
The conjugated part
So 2 root d over a.
over a. So this is going to be a root d over a to the s power.
That's where we're going to get our root d to the s.
Very interesting. Okay, let's keep going. Let's keep going. So I'm continuing the calculation here. I'll pull out the root d to the s. I have a sum over q in xd mod gamma, a sum over gamma, by which I mean now CD or coprime. Right? This gamma is whatever CD. So it's just whatever the bottom rows are. Here, the determinant, okay, I have a 1 over a to the S. That's from this A. That's the determinant of G to the S. Okay, so the E to the U, I'm going to move downstairs in two parts. I'll move it as a E to the U over 2 squared with a minus sign.
It's gonna start looking like that's not
So I
the
haven't,
length of the,
right. So I have, and by the way, what is the absolute value squared? This is real. This is real times I.
that's just gonna be.
So it's just going to be the square of this and the square of this. So let's keep track of that. It's going to be C alpha plus D squared times E to the U over 2 squared plus C alpha bar plus D squared times E to the minus U. And all of this is raised to the S power. And then we're integrating. I lost my integral. There's an integral from 0 to L to the length D.
Wait, wasn't your gonna go like?
Yeah, it depends on if you want to pull it out or pull it in. I don't know. I whatever it is, I wanted these two things together.
Okay.
Okay. Now this is not a nice integral to work out in U. It can be worked out. It's a horrible hypergeometric series, but there's something much nicer that we could do, which is to remember our unfolding. So in fact, all the way back here, we could, this was just to see that, yes, it's like a, it's some kind of quasi, so we get C alpha plus D squared, which isn't quite Q of CD. The A, by the way, the A can get pulled into all of these things and give you, you know, what am I trying to say? I'm trying to say that Q of X comma 1 is A times X minus alpha times X minus alpha bar.
Oh.
I'm just reminding you that if you set Y equal to 1, Q is a quadratic form in two variables. If you pull out the leading coefficient, now you have a monic polynomial, monic quadratic, which is X minus the product of X minus 3's. Okay, so multiplying by A will give us exactly Q. If we had, this is like X minus alpha. So in other words, if I put the Y back in, I get X minus alpha Y, X minus alpha bar Y. So this is exactly, this is going to turn into some, it would turn into a quadratic, except this has an alpha squared, this has an alpha bar squared, and they have these E to the U's and E to the minus U's in front of them.
Yeah.
So it's a little bit complicated to work this out.
Pseudo hyperbolic design or something.
Right. Instead, we can go back here. Instead, we can go back here.
Why do we keep going forwards and backwards?
Because I'm not giving you the streamlined presentation. I'm giving you the, like, what's the natural thing to do next? It could be to think of it this way. It could be to think of it that way.
But what mileage did we get from the last unfolding?
It's the thing that most closely resembles what we did when we were doing Heegner points instead of closed geodesics.
Okay.
Okay. But at this point, yes, let's remember the fact that gamma acting on G is exactly G of Q composed with gamma inverse. So we can unfold these two sums together. We have exactly what we saw before. Q was in XD mod gamma. This is gamma in gamma mod gamma infinity. So those two sums together, can I fit them all on? Okay, I have to write down here. Will give us a sum over Q in XD mod gamma infinity, right? Which was this classes, if you remember what this, we said what this was. It was the ABCs. Right. Exactly. With B squared minus 4AC equal to D. And B is determined mod 2C, or equivalently, because there's a complete symmetry on these, B is determined mod B is determined mod B is in Z mod 2A. Doesn't matter if you use A or C for this equivalence class. And there's a root D to the S. There's a 1 over A to the S, which is why I'm isolating A. And then there's this whole imaginary part, but just with Q, with no CD. In other words, with C equal to 0 and D equal to 1. Exactly as we had before. This is trying to evaluate things at C and D, but now we can evaluate this at C equals to 0, at CD equal to 0, 1, if we unfold. CD equal to 0, 1. In other words, pretend that the Q that we were applying it to, so when we had Q composed with gamma, the composition with gamma was this CD. But now when we unfold, we can take the identity coset.
Oh, so you're saying like, this is what we would normally get, had we just done this, but instead we can just do it all at once?
We can, yeah, we can starting from here and using the fact that this is G of Q composed with gamma inverse, unfold, and we get this same imaginary part, but now with no gamma. In other words, where gamma is the identity. Let me say that again. Instead of summing over Q only up to SL2Z equivalence, which is many more things are being thrown into one class. And so much so that this is a finite set. This is an infinite set. Okay, so I'll group things much less. So now I have an infinite collection here, but now there's only the identity coset here. So the identity is when C is equal to 0 and D is equal to 1. We don't have to redo any calculations. We can go straight to this calculation and set C equal to 0 and D equal to 1. Okay. That's right. We have something that's 1 over e to the u plus 1 over plus e to the minus u to the s du.
Yeah, and that's just-
But this doesn't depend on Q. So it just pulls out. This pulls out.
then I get this beta.
This pulls out. And by the same reason as before, this comes to, this is a root d to the s times this integral. Let me call this integral I. And then we have this sum. And this sum is exactly as before, zeta of s, L, this is the L of s cut.
Wait, and then why was this true again? Yeah, sum of 1 over a to the s giving us
Oh,
zeta s.
right. So we reviewed that at the beginning. It's that this is the number of representatives. So if we group them by C's
Or a.
or A's, same thing, then we want to know how many representations there are of B's, which only range mod 2C or mod 2A, with this- yeah, which is a sum over chi's. And then when we unfolded that sum, we get this Dirichlet zeta function. Okay. And now we're done. And now we're done. Now we take residues. This thing gives us L S chi. This thing gives us our root D. This is a constant. So we get root D times L1 chi on this side. On the other side, we got class number times regulator. H of D times log epsilon. And
The
that,
regulator was coming up because
because it was the length.
it was a length,
Yeah.
we set up the integral differently.
Well, we had to integrate over the closed geodesics. So this was a length. And the residue is a constant. So the length exactly turns into this log epsilon. Yes. Well, I'm dropping constants in a bunch of places.
The integral, what, this is like integral of hyperbolic secant or something.
Yeah, it's a little annoying, but it's just some constant.
And do we know anything about that constant?
We do, you can work, yeah, so we do because we have this point. So by other means, I'm sort of running out of time to really analyze this integral properly. But by there are other proofs. I mean, we don't want to rely on other proofs. Yeah. In the interest of time, let me not analyze this integral. But one needs to in order to make sense of this. If we just want to prove that something's non-zero, then this is enough.
Okay, so it's fine.
Yeah.
But in practice, what is this equal to without proof?
Yeah, so I think the constant here is actually 1. I think all the constants actually cancel. And in the real case, in the real quadratics, you literally get class number regulator over root discriminant.
Somehow this integral is going to cancel out the pi over 6, whatever.
Yeah. You have to be a little bit careful here which class number you mean. In the wide sense or in the narrow sense, there might be a factor of 2. When you see this in the literature, you have to say, wait, class number up to SL2Z or up to GL2Z.
This I depends on the.
Yeah.
I don't know what to do.
Yeah. Well, something's.
Yeah, you're right.
Something's funny.
Sorry, what was the question?
You're taking a residue.
This has a D in it.
And it has an S in it too, when you're taking a residue.
Well, the S I'm not so bothered by. I just sent S to 1. I think this is regular at S equals 1.
Wait, but then that means that you can evaluate this directly. There's no, I don't think there's any.
Yeah, but it has a D in it, and I don't want it to. Louis, sorry, go ahead.
Oh, I was just gonna. Originally, I was gonna say about S2 that it really should be like I of S, but then S goes to 1 and it should be fine, right? So that part. Yeah.
It's an I of S, and when we take the residue, the S goes to 1.
And I was also, I think you're right about L1 chi, because I think the pi should come from like complex embeddings. So I think that there shouldn't be pi's, maybe factor 2 if, like you said, like narrow or wide, but yeah.
No, but now I'm bothered by the fact that there's a D in here.
Yeah. Right. Yeah, that's a good point.
Let's see. I don't really have, I mean, I made little sketches to myself for how this should go.
There's no expression for L.
There is LD, but we don't want it. I mean, we know what LD is. LD is right here. Yeah, there shouldn't be. LD is 2 log epsilon D. It's exactly where this came from. It's right here. LD is 2 log epsilon D.
Oh, and you're worried about having the regulator on both sides?
I mean, this should be the clean formula. The I should be, in my mind, the I was just 1, or some finite constant, but no, there's a D in there. And this should be the actual formula with the D's. There shouldn't be any other D dependence, but this seems to have a D dependence. So something's wrong. Yeah, maybe time will be my mercy.